Today I want to share with you still a concept in gravitational physics or in astrophysics, which is called energy of a satellite or energy of terrestrial bodies in the atmosphere. So we are going to start from what we call gravitational potential. Gravitational potential. In this sense, we are going to look at what we can do to move a body of 1 kilogram from infinity to a point within the gravitational field of a given planet. So that's the definition of what we call gravitational potential. So in this case, we want to assume that you have a mass of a body of small m, which is 1 kilogram. Then you have capital M, which could be mass of the planet that controls that body. With this, the force of attraction from Newton's law of universal gravitation is capital GMM out of R squared. But since we have identified small m as 1 kilogram, then this is going to be capital GM out of R squared. Therefore, the work done, if this is the controlling planet and the body was initially a distance r away from the center of the planet, then when we move this body from infinity through a small change in distance r up to this point A within the gravitational field of this planet, then we shall be doing a small change in work done, which is equal to force times a small change in the distance covered. Now, to get the total work done is going to be equal to the integral of the work done, dW, from no work done to some work done, which is going to be the integral from infinity to a point, a distance r, within the gravitational field of a given planet, then integrate that force with respect to r, the distance of separation between the movable body, which body was of mass 1 kilogram, and the mass of the planet. Potential is cutting across so many sections in physics. Potential cuts across in electrostatics, we have electric potential. Potential cuts across in gravitational physics or space physics, astrophysics, we have what we call gravitational potential. Then also we have potential of an electron under the Bohr atom sections. When you're looking at energy of an electron in an atom, there's a point where we have potential or work done to move an electron, which work done to move an electron is also negative. Here also potential will be negative, even in electrostat, work done is negative. Now, the idea is the same. We move items from infinity to a given region or to a given point, some distance away from the reference point. So here we are looking at a point of moving a body of mass m from a point B prime at infinity. This is at infinity. Then move it through a small distance r, carry r or delta r. Then the total work done will be W is equal to the integral from infinity to a point, a distance r of f dr. It is from here that now we can substitute the function for force as per Newton's law of gravitation. From Newton's law, the total work done will be the integral from infinity to r of f, which f we have seen is capital GM out of r squared with respect to r. This will be the same as if you factorize capital GM, you'll have integral from infinity to r of 1 out of r squared dr. When you integrate 1 out of r squared, the result is a negative gm out of r from infinity to a point, a distance r. When we substitute the limits, we shall have a negative gm into brackets 1 out of r minus 1 over infinity. But 1 over infinity is 0. Because when you divide something very, very big by something very, very small, then this very big item will tend towards 0. So that's why the solution tends to 0. So therefore, the work done, which is the potential, is equal to a negative gm out of R. So the potential V, normally we call it V, is equal to a negative gm out of R. And this is the potential for a mass of 1 kilogram that has been moved from infinity to a point, a distance R, within the gravitational field of a given planet. Whereas for n kilograms, for small m is equal to n kilograms, n kgs, we get what we call gravitational potential energy. Which is going to be equal to a negative capital Gm small m mass of that body divided by the distance r. So with this gives you what we call the gravitational potential energy possessed by a body of mass m kilograms, which mass is greater than 1 kg. That is 1 kg being attracted by a planet of mass capital M. So in total, potential energy is always given by a negative GMM out of R. This is always the potential energy of a body of a given mass, small m. If it's a satellite, then it is potential energy of a satellite, and we assume the satellite of the mass of the satellite is small m, and then we assume the mass of the planet is very big M. For example, if you take a look at our satellite of our country, Uganda, Pearl of Africa Satellite 1, the mass of Pearl of Africa Satellite 1 can be small m, then the mass of the planet Earth is capital M. So the potential that satellite has in the space where it is, if it is here, and this is the Earth, and our satellite 1 is here, S1, the height where it is plus the radius of the Earth will give you the total radius of the satellite from the center of the Earth. So this is the radius from the center of the Earth, R. It is this R that we substitute in that expression to realize what we call the gravitational potential of our satellite when it is up there in space, in its given orbit. So R is basically the radius of the orbit of the satellite or of the body once it is coming from the center, or once it is measured from the reference center of that planet, which controls that satellite. With that, today we have discussed what we call gravitational potential, and from it we have induced what we call gravitational potential energy. This is still more on gravitational physics and astrophysics, so join us, stay with us so that you can have more illustrations and more presentations in physics and in this area of gravitational physics. Have a good one.